India wants to be a semiconductor powerhouse.
Semiconductor. Semiconductor.
So what exactly comes to your mind when you think of semiconductors? So this is a gallium nitride semiconductor, and I'm talking about it like I know what that means. This little wafer has tiny chips in it that go into defense and telecom systems. And honestly, it's hard to believe that something this small ends up powering systems that run entire countries. But here's the reality. India imports more than 90% of its high-power semiconductor chips. Last year alone, India imported semiconductor chips worth 1.7 lakh crore. Now to rewind a little, if you open up almost any electronic device from the last 50 years, you'll find the same material at its core, that is silicon. It's in your phone, your laptop, your car, almost everything. But silicon is starting to hit its limits, especially in places that need high power, high speed and high efficiency. And that's where this tiny material comes in. That's gallium nitride or GaN. GaN can handle more power, switch faster, run cooler, and shrink equipment by up to 40%. Now all of this seems like very important technology. So we decided to do what we do best and go meet the people who are actually working on this. I reached out to the team at Agnit, and they are trying to build gallium nitride chips right here in India. One thing led to another, and a few days later we were here at IISc, where this technology has been worked on for years. So in this video, I try to understand two things. Why is India betting on advanced chips like GaN? And why are we doing this now? That's exactly what we're here to find out. Why not go figure it out together? So let's go. Welcome to Agnit. To really understand how Agnit came together, you have to zoom out a bit. Long before there was a company, this work was already happening here, inside of a university lab. At IISc, GaN research had been going on for over 15 years. Over time, that work added up, and several people who would later go on to start Agnit were part of that effort. And now we are at the IISc building. It is a beautiful building. And you are a student here? Tell us a bit more about that.
Sure. I did my bachelor's in electronics and communication engineering. Then I spent a year working at IBM. I was a silicon chip designer. And so after a year, I thought that I really need to upskill. And, what I wanted to do was, be involved in kind of the architecture of certain products as opposed to implementing few things. So I thought that joining IISc was kind of a no-brainer at that point of time. So I applied and I was lucky to get in. And so that's how I got started. So I did a master's and a PhD in compound semiconductors, gallium nitride specifically. So, I've been working on this technology since 2009 when I joined IISc. And it's been about 15 years of working on this now. So for me.
How exactly did IISc help Agnit in the early days? Deep tech startups usually struggle with funding, infrastructure.
That's true.
How did they help?
So at IISc, the gallium nitride research kicked off in about the year 2006, 2007. Right. So we finally started operations in Agnit in 2021. So we had about 15 years worth of developing this technology, getting it to a stage where we thought, okay, this might be commercially viable, right? And there was an interdisciplinary team of scientists and professors, about more than about 10 professors and bunch of researchers. So that's the kind of deep know-how and just doing things on the ground that it takes to get to a point where you think something might be commercially viable, right? And even then, the commercial viability is still something to be proven, right? So you need that very strong technology base to get started. And so in that sense, without IISc support, I don't think we could have done what we are doing now. But when we started, we had more than a dozen patents licensed from IISc, which is all the technology that the founders of Agnit had created over many years. Right. And that kind of support was very, very critical. And the fact that we are incubated here, you have access to a ready pipeline of talent. So it will take you anywhere between 2 years to 3 years just to get your first chip out. And then you have to get that validated out with customers. The first 2-3 chips that you make will always be hard. And after that, you do have some kind of a flywheel. So it becomes easier as you go forward. Right.
So what exactly gave you that confidence to say, okay, this could be turned into a company?
It was a need of the hours. Firstly, India needing a semiconductor IP and manufacturing ecosystem as well. So that was one. Secondly, if you take a look at the technology, right? So the technology is, gallium nitride technology is at a stage where, you are starting to see adoption into a wide variety of use cases. And thirdly, somebody has to take a chance somewhere, right? So we decided that since we are conversant with the technology, and we had a lot of customer conversations before we started the company as well. And when we understood the pain point and thought that, look, this is some value that we can deliver, right? These are the kind of components that are missing in the ecosystem for various reasons. I think that in turn gave us a little bit more business confidence as well. So at that point, we said, okay, there is a real need for what we are trying to do.
For years, India's role in semiconductors sat mostly on the design side. Engineers here helped design the chips, but they were made mainly in East Asia, which today controls more than 70% of global chip manufacturing. In 2020 though, when supply chains broke down, chips suddenly became hard to get. Car factories slowed, electronics were delayed, and it became clear how dependent everything had become on a very small number of places. Since then, semiconductors have moved from being background components to critical infrastructure. Chips now sit inside telecom networks, power systems, electric vehicles, and defense hardware where delays or restrictions can have real consequences. And is the government being supportive to enable all of that?
The government is being extremely supportive. I think part of the reason that you see the kind of activity in the space that you do, whether from startups or from investors, is that, things like the India Semiconductor Mission have been extremely positive steps forward. And you will also notice they are long-term initiatives. A 1-2 year effort is not going to cut it. And I think that people are starting to realize that, especially in terms of policy push, the government is serious and they are doing things on the ground which actually support this multi-decadal ambition that we have to sort of plug into the global semiconductor value chain at the end of the day. That's what we want to do, right? It's of course, government is the big driver. And in many things like, manufacturing especially, even if historically, if you look at it for various countries, it's the government that actually starts this off, right? Because the amount of capital involved is actually quite large when you start out with. So the things that they've given in terms of policy initiatives, subsidies for setting up manufacturing plants, all of these are very critical, without which this ecosystem really wouldn't take off. But in order to get it off the ground, it's the government that needs to do a lot of the heavy lifting, which they are starting to do now.
The deeper I went into this, the more one question kept coming back. Where does India actually stand in the global chip race? Up to this point, everything we had seen explained how the technology came together and why building it inside India is even possible. But the moment you step outside a lab and into the real world, the questions really start changing. How late or early is India to this moment? And once a chip leaves the lab, who's willing to rely on it? So India is a little late to the semiconductor race, right? So realistically, how long before we get there?
Okay, I would have a different opinion on that. India is not actually very late, especially considering the fact that our semiconductor manufacturing initiative started in the early 80s. It just happened that it ran into a few obstacles and hence we fell behind. But India was way ahead. It was ahead of Taiwan as far as semiconductor manufacturing is concerned. But having said that, it is catching up rapidly. There are a lot of initiatives with the help of the government which have come up. And I think at the rate that we are going, and if we target specific industries, specific applications, specific materials, I don't think that we would say we have to do any amount of catching up. I think we are already in that particular position.
Imagine a made in India semiconductors. Will people find it difficult to trust a semiconductor chip that is made in India?
I don't think so. Given the fact that quite a lot of made in India semiconductor products have already been starting to get accepted in India. We are talking of the navigation chip, which already ISRO is using. So there is an acceptance, and I think the good thing is the way the government has brought in the level of branding and visibility of the semiconductors across the spectrum. Now almost everyone talks of semiconductors, whether they are in that domain or not. So I don't think acceptance is really going to be an issue. But what is probably going to be very critical is the reliability of the semiconductor chips that come in and the way they work for a long time. If that hurdle is crossed, and I'll say hurdle because we are doing it for the first time or we are in the initial stages. But once we do that, I don't think there is going to be any sort of a reluctance in accepting the made in India chips. And I wouldn't be very surprised if even outside of India, these chips start getting accepted.
So far, the story has felt very high-tech, but GaN isn't some sci-fi material waiting for its big moment. It's already doing real work in everyday life. You just don't see it. And once you know where to look, it's pretty much everywhere. What kind of equipments or devices do people use gallium nitride in without even knowing that they're using it?
Oh, so the most common example is your light emitting diode. Almost every one of us has bought a white LED bulb and there is gallium nitride in it. We are all consuming energy in the form of electricity. So if you bought a compact cell phone charger And if you look closely, there's a very good chance it will say GaN inside. Okay, so these are the two common applications from everyday life that I can think of. But another very important area that's coming up is, for example, radars. Everybody has seen radars, and it's used for, defense applications, and that is also where you need GaN. And that is an example of a wireless application. But that apart, even in your cell phone towers, if you have to communicate wirelessly, you need gallium nitride.
These are some of the products that we make today at Agnit. And so just to give you a walkthrough, so this is a bare silicon wafer. This display is primarily for power electronics. This is a bare silicon wafer. You take the silicon wafer, we grow a few micrometers of gallium nitride film on top of this. And once you do that, then it runs through hundreds of semiconductor processing steps in order to get from a blank gallium nitride wafer ready for processing to a fully processed wafer. Each of those gray squares that you see there is a chip. Right? And then of course you can cut it up and then you can package them, put them into these sort of packages. And then you can put this on a module like this. So this, for example, is a DC-DC converter. It takes 48 volts of input DC voltage and steps it down to 5 volts. Right? So this kind of size reduction is really what is the story of your fast charger if you think about it. Right? So
that is interesting. And you start with a silicon base, right? And then...
That's correct. We start with the silicon wafer and then we put GaN on silicon, and mainly for cost reasons, right? Silicon now is very cheap. So these are all what you see here on here are about 2-inch in diameter. That's where we started.
How many types do you have?
We have 4 and 6, that's it.
4 and 6?
Yeah, just
okay. Okay, and how many chips can be made on the 4-inch one and the 6-inch?
It depends on the kind of chip you're making. For example, if you make these kind of chips, then on a 6-inch wafer, you could make about 3,000 of these. Right? So of course, if you want to make a chip, let's say for something like a fast charger, for an EV fast charger, then you'll make about 2,500 of them on a wafer. It depends entirely on the size of the chip and the functionality you want it to implement.
And how much is one chip worth?
So it depends entirely on what sort of chips you make. Some of the wafers that we showed you earlier, right? So that could cost anywhere upwards of $100,000 the first time you make it, right? So those are these engineering wafers that you run. So after that, you can, with volumes, normally the production costs will come down. But yeah, that's a good ballpark for how much it is. So then it's a question of how many chips have you packed on there, right? So these are like, to set things up and going, it's an expensive proposition. Once it's up, I think your economy of scale kicks in, and then it makes the cost a lot more reasonable for anybody who wants to, for any customer who wants to adopt it. Gallium nitride today is more expensive than silicon. So that's something that we went over earlier, and that's something that's going to stay, right? So ideally, you want the performance of gallium nitride at the price of silicon. We are not there yet today, but we may be there, let's say about 3 to 5 years down the line, based on how manufacturing evolves here.
At this point, it's easy to assume that gallium nitride is meant to replace silicon. But that's not the case here. Silicon still does most of the heavy lifting in computing, memory, and everyday electronics. Gallium nitride shows up only when the demands change, when systems need to handle much higher power, switch faster, waste less energy, and do all of that in a much smaller space. In those situations, silicon starts to struggle, and that's exactly where GaN comes in. So when you think of semiconductors, you mostly end up thinking silicon. So when did that start changing? How did GaN come into the picture?
Actually, silicon is still the predominant semiconductor of our age, right? So like I said, a lot of the logic and memory stuff is still, all the chips are still being made on silicon, right? Now, in terms of chips which handle power, whether it's power electronics, which is in all the fast chargers that we use, right? So you'll find GaN-powered chargers, fast chargers today. In systems which use wireless electronics, it turns out that gallium nitride as a material is superior to silicon in terms of handling power, right? This is due to a bunch of material properties that gallium nitride has. Now, gallium nitride has material properties that for comparable like-to-like comparison when compared to silicon, it can block 3 times the amount of voltage, right? When compared to silicon. So it can also conduct electrons about twice as fast as silicon. So these are the properties that makes gallium nitride as a material superior to silicon, and therefore used in all these discrete use cases. Logic and memory is still going to be on silicon, and it continues to be on silicon.
But then it must be a little expensive to make, right? Does that make the final product cheaper or something?
That's a very interesting question. So today, gallium nitride is definitely more expensive to make than a silicon, right? Comparable silicon part. But the functionality that delivers, for example, let's say you want a compact, efficient fast charger, you're going to pick gallium nitride, right? If you want something that's, sort of more bulky, etc., you can go for silicon. But now you can see that there is a very clear, customer pain point that you're solving. You have a compact charger, which can charge your phone in 20 minutes, right, which was not the case earlier, right? So those are the kind of value additions that's happening at the system level. At a component level, yeah, gallium nitride is more expensive than silicon. But if you take a look at it in terms of the bill of materials in any system, and if you take a look at the cost of ownership, then all of that is, is a no-brainer for adoption of gallium nitride in certain use cases.
Making one chip is easy. The real challenge is making the same chip the same way again and again and knowing it will behave exactly as expected every single time. That's the gap India is trying to close right now. For that, the government has sanctioned around 300 crores to set up a gallium nitride incubator at IISc Bangalore. It's a clear attempt to move GaN out of research labs and into a repeatable supply pipeline. What will it take for us to reach a scale where gallium nitride is used by almost every other industry in India? Like, what will it take to get there?
So gallium nitride is an upcoming material, right? Trying to replace the conventional traditional silicon technology, but we are using the same process technology to make those. So that is a major advantage. Though we are using a completely different material system, you need to be innovative in creating this process technology to do this, right? So there is a difference between, buying a product from a novelty shop and going and stepping into IKEA and then looking at the same product in large numbers, right? So you may like the product from the novelty shop, but you want, your friend to have it, your family to have it. If you go back, it's gone, it's not there, right? So the translation from the novelty shop to a more mass manufacturing, what is the difference there? And that is the difference, what we are trying to bridge here. So the fabrication facility that we have here is a pilot line that will help us to make, for example, a wafer like this, right? Where there are, hundreds and thousands of devices that we can use to do a proof of concept that integrating 100 process steps, right, to get to a device. But then this is only one wafer, right? But if I want to have thousands of such wafers, I need a technology that can churn out this 100 wafers repeatably. Every device, every wafer should yield the same, right? That is the gap we need to bridge, right? So this is good for proof of concept, low volume you can say, but then if you want to translate this to a mass manufacturable, ecosystem, you need a dedicated foundry at a larger scale, right? The challenge there is the same challenge like building a small house, right? And building a big, a complex, a mall complex, for example, right? The problems are very different, but it's still same civil engineering knowledge that you are going to use. The same thing applies here as well. Yielding a small die or a small wafer may not be challenging, but the moment you talk about large wafer scale, you have to improve your chemistry, you have to find different tools, right? Process tools that can yield you. So identifying the right process, identifying the right tool system becomes essential. So in India, we have a huge market for gallium nitride technology, but all we need to do is to build from the success that we have today and bridge this, scaling gap, and we should be able to cater to all the market that we have, from charging your cell phones to actually the cell phone tower, right? Will also have gallium nitride technology.
Making chips is expensive science. In India, setting up even a mid-scale semiconductor lab can cost up to $5 to $8 billion, while most deep tech startups only start with a few $1 million in funding. This is exactly where the government steps in. The idea is pretty simple. If the biggest and the riskiest part of the investment are shared, companies can focus on what they actually control, which is getting the technology to work, refining it, and making it reliable. So this is a very capital intensive business, right? And you've only raised $5 million as of now, but you of course have backing from IISc. But how are you able to do so much with so little?
The Ministry of Electronics and IT has funded this particular facility to be a gallium nitride, it's called a gallium nitride ecosystem enabling center and incubator, GECI, or GEEKI for short, right? So this is a small volume foundry that's able to support startups like Agnit, right? So today, if you have to actually go out and have a conversation with, let's say, investors, etc., to raise $50 million, let's say close to $50 million with no products and, no revenue, it's a tall ask. right? So, and in countries all over the world, you'll realize that governments have actually stepped in and supported the semiconductor sector in the initial years. And then, of course, all of this is then translated, so the scale up becomes a lot easier. But right now, you have a 0 to 1 transition to make. So, we are not raising money for infrastructure, right? So, as part of Agnit, what we do is we raise money mainly for our technology and product development. So, now it's up to startups like Agnit to actually use this infrastructure and make sure that technology that we've developed indigenously is actually production worthy and you can actually put chips in the hands of customers. So, it's the technology translation that's important, and that's what the facility is also geared towards doing, right? So, which is a very forward-thinking initiative by the government.
A chip that keeps phone network stable has to behave very differently from one used in defense systems. Once a chip is built, the next question is where it actually ends up. Not all chips are designed for the same job. That is exactly what we wanted to understand next. When you make the gallium nitride chips for telecom and for defense, are they made differently to fit each use case?
That's a very good question. The device itself may have some differences, but the way you configure the device for the final system is very different. So telecom looks at something called linearity significantly, because when you talk and there's so many channels, right, there should not be distortion when one person talks to another, and you can have overlap from other frequencies, other channels. So that linearity is a very important aspect. In military sector, that is not so much important because you don't communicate as much. You do, but primarily as a radar. You want to detect an enemy ship or plane, or as a drone jammer. There you are concerned with high power. You blast high power to damage or jam the enemy thing, which is not the case in telecom. They cannot blast high power. It is environmentally not allowed by the government, right? So the device has to be designed slightly differently, but more than that, the system has to be designed much differently. So yes, there's a difference.
I walked in here not knowing what a semiconductor is, but now that I look at it, I see how much of India's future actually depends on it. We have a lot of new technology coming up. There is ChatGPT, there's AI, but then you need something that is going to make these devices faster and a lot more efficient. That is exactly what Agnit is trying to do here. Of course, it's going to take more time. Of course, it's difficult to hire people. Of course, it is capital intensive, and it's going to take a lot of patience for us to get there. But for them, this is business.